What are race conditions? To put it simply, take a social media post. Aside from having a title and a description, the author's tags, a post has likes. Now imagine two people liking the post at the same time. And let's say you have, well, an endpoint for liking a post. What is the logic going to be for liking a post? Well, what you're going to do is query the database, look for this particular post, then get the previous likes, and then add one and update the row. So here you have two operations, one for querying, the other for updating the row. But what happens if these two operations occur simultaneously? They are likely to read stale data. So we have user 1 added a like, and then user 2 added a like, but they hit the button at the same time, and so the server starts this logic at pretty much the same time. Obviously, it might be a couple of milliseconds of difference, but writing to the database can take up some time. So the two are querying for the data, they both get like 0, and then let's say this request for user 2 updated the data, so now likes are 1. Well, the request belonging to user 1 doesn't know that this was updated to 1, so it is basing it off like 0, and then it is going to add 1 to it and update the row. So what is going to be the resulting value? Well, it's going to be 1. Yes, two people like the post, so it should be 2, but due to race conditions, it is now only 1 like. Now potentially think of a scenario of 500 concurrent requests. The resulting value is going to be way off. Instead of just being 1 like, so you say, okay, the user liked the post, but a difference of 1 is negligible. But now 500 users hit the database at the same time, and instead of having 500 likes, you now have potentially 30 likes. And that's no bueno. So how can you avoid race conditions? Well, let's take a look at the sample code. So here I have this basic model. So we have a table for posts, we have the views, so we want to track how many people have seen a post, similar to Reddit where you have that analytics tab and it is going to show you how many people have viewed your post. And then we have the title, the ID, which is auto increment, so just an integer, and then body, and then created ad. So nothing complex. So every time someone wants to see the information for a particular post, what we're going to do, aside from, well, returning the post, we're going to increment the views. So here we have the ID, and then we get that parameter, we check if it's a number, if not just by request, and if we have a valid post ID, we query the database, where the ID is equal to the one passed in, and we retrieve the ID and the views. We make sure that it exists, of course, and then we update the post. So we say update table posts, we set the views to be post.views plus 1, where post ID is equal to this one, and we return the ID, the views, and well, of course, here we could return the body, the title, and create an ad. And then we just respond with a JSON of the post. So again, this is for when a user opens up a post. We automatically, behind the scenes, increment the views by 1. So now let's give it a try. Let's see what happens if we retrieve a post. So we say curl, then next for the method, we say get, and we pass in localhost 3000, and I pass in the ID of 1. And that's because I'm setting the database and I'm just passing in a single row. So hello world, and this is a test post. And well, since it is auto incrementing, it is going to be 1 for the first row. And if I run this, as we can see, we have views 1. That makes sense, right? Because, well, we just viewed the post, and this is the first time anyone has ever viewed the post. What happens if we do it a second time? As we can see, views 2, a third time, views 3, and so on and so forth. But now let's simulate a lot of people viewing this post. For this, I'm going to be using the Apache utils, so the AB command, which works for benchmarking your server. So what we can do is we can say AB, then -n, then 100. So we can say the amount of requests we want to perform to the server, and then we can pass in the concurrency flag. So this is going to perform the requests in batches, in concurrent batches. So if we say 10, it is going to perform 10 different batches consisting of, well, 10 requests. So 10, and then I pass in the endpoint. If we do this and I hit enter, as we can see, we have all of the batches. But now, if we retrieve this post, theoretically speaking, we should have 103 views. But as we can see, we have 44. So again, this is because of the race conditions. Since these two operations, so reading the post and updating the post, are not entirely sequential, many requests will reach this point, just read the post, and then they are going to start updating the database. So they are reading stale data, which means data that is old, that doesn't represent the current state. So what exactly can we do to prevent this? How can we prevent race conditions? Well, for this, you may have heard of using transactions with your database. Now, if you're not familiarized with transactions, well, they are just operations aggregated, so grouped together into a single operation. That way, let's say you want to update a row, delete another row, and create another row, but they are all dependent on each other. You can just use a transaction, and what it is going to do is it is going to ensure that either all of those operations, so creating, deleting, and updated, succeed and are applied to the database, which is known as committed to the database, or none of them are applied. So let's say there was an error deleting that row, then it is going to reverse back the state of the updates and the creation, instead of, well, leaving those dangling rows with data that most likely shouldn't exist. So within these transactions, we have isolation levels. So they are basically different rules that you can configure your transactions to use. And for that, we have 5. So we have read uncommitted, read committed, repeatable read, serializable, and finally snapshot. So let's go one by one and see which one could help our case. So the first one is read uncommitted. So it is a transaction that may read data that is being written by another transaction that has not yet been committed. Now again, when I'm talking about committing is when the transaction updates the rows, so it performs the necessary changes. But well, if there's an error, then it is going to be uncommitted. It is going to reverse everything. But if everything went okay, it is going to commit those changes to the database. So this essentially means that even though there's another transaction taking place, it is still going to read the data even if it's being written by the other transaction. So this causes the database to read stale data, and it is going to commit changes that do not reflect the real value. Now, this is useful if you want speed over accuracy. But well, these textbook definitions don't really tell us much. So let's take our example. So say we have the two users making the request. So we have user A and we have user B. Now user A retrieves the post. So it gets the post with the likes of 10, for example. Now at the same time, user B retrieves the same post and sees that it has 10 likes as well. Now the transaction reads this and it is going to increment it, so likes plus equal 1, and it is going to do the same with the user B, so plus equals 1. Now the final like count is 11, not 12 as you would expect. So this makes sense because this isolation level doesn't care that that data is being committed by another transaction. So it's just going to continue its course as if nothing happened, which is basically what we're getting right now. We're not using a transaction, but this would be the same behavior. Now let's move on to read committed. So read committed, a transaction can only read data that has been committed by other transactions. So what's the benefit of doing this? Well, you avoid dirty reads. Now when we talk about dirty reads, we are talking about this one, for example, where we just read the data once. So we query the database once, we get the data, and then we perform the rest as we please. We do not care about anything else. Well, this is going to prevent this from happening altogether, but it is going to do phantom reads. Now, when we talk about phantom reads, that means that this transaction is going to reread the data over and over again, just to make sure that, well, we're getting the most recent data. So it looks for if some rows have been added or if the existing rows have been deleted by another transaction in the meantime, which makes sense if you think about it, because, well, it is only going to read data that has been committed by other transactions. So to ensure this behavior, it is going to use phantom reads, which might be a con if you do not want these extra reads to the database. So going back to our example, by using the read committed isolation level, then user A retrieves the likes. So it sees that it has 10 likes, and then user B tries to retrieve the same post. But it notices that there is another transaction in place, so the transaction for user A. And so it is going to wait. So this one is going to wait until transaction A has been committed, basically. So it is going to increment the likes to 11. And then user B sees that it has finished committing, so it can now read again, checks that the likes are now 11, so it is going to take it from 11. So this is actually the other way around. And so the final like count is going to be 12, which is what we would expect. So now let's move on to the third one, so repeatable read. A transaction can only read data that has not been modified by other transactions since the start of the current transaction. So the benefits, you want to ensure that data will not change during the course of a transaction. So let's see this in action. So we begin, so begins with user A. Let me make this a little smaller. So begins user A. This user sees that it has 10 likes and it is going to increment it by 1. Now user B simultaneously also begins another transaction, so begins user B. And since the start of the transaction, it retrieved the post, but it sees the old likes count, so 10, and then it is going to increment it by 1 regardless. So this is going to cause an issue where we're seeing these data races. So again, this is based off the fact it is going to read data that has not been modified by other transactions since the start of that transaction. It doesn't care about the other ones in that way, as well the read committed does, which is going to perform the phantom reads. And this one can be compared to the first one, so read uncommitted. Meanwhile, this is repeatable read. So again, read uncommitted, even if another transaction started and it made some changes that could potentially be rolled back, this one doesn't care about that. It is still going to read those uncommitted changes and it is going to use them as the basis, which is extremely error prone. And in fact, I've never seen this in production. I'm not sure in what cases this would make sense, but with anything, I'm pretty sure there's a very specific scenario where this might make sense. This is just like the equivalent, but instead of reading uncommitted, it makes sure to just read the committed. So it is way less error prone. And in fact, you would see this way more often compared to read uncommitted. This is like the better read uncommitted. Okay, so now let's move on to serializable. Prevents dirty reads, so that's great. Non-repeatable reads and the phantom reads. So this is for when you want full isolation between transactions. Now the problem is it is going to basically lock down those rows. So no other transaction can take place when a transaction with serializable isolation is taking place. So this allows you to basically prevent stale data. And well, there's no need for phantom reads to make sure that it is the most updated as opposed to read committed. But again, the con is it locks more rows, so it might not be ideal. And in fact, you shouldn't be using these in high traffic rows because it is going to hurt down the performance of your database by a lot, since it is going to cause a deadlock and nothing else can access it until it is well released. So here, when this begins, so we have the transaction for user A, this one is going to lock down the rows. And so it gets likes 10, increments it by 1, and then I just noticed this typo. User B now can start updating the data, so now it retrieves 11 and increments it by 1. So we get 12. But what about the last one? So we have the snapshot isolation level. Well, this one does a snapshot of the data at the start of the transaction. The transaction can read from this snapshot without worrying about other transactions modifying the data. And this is if you want to ensure consistent reads without locking rows. But well, the consistent read is based off what it got from when it performed or created the snapshot. So it could also potentially lead to stale data. But how does a snapshot look like in practice? So here, user A begins the transaction, retrieves a snapshot of the post, so 10 likes, and then user B starts another transaction and retrieves the snapshot of the post with 10 likes. So these two have 10 likes at the same time, assuming well the requests came at the same time. And then both user A and user B will try to increment the like count. And then they are going to commit the changes to the database. Now here's a conflict. So this causes a conflict. Why? Because, well, this one updated the row and then this one updated the exact same row. So the database might raise an error in one of the transactions saying, hey, well, your snapshot is outdated. Or depending on the database driver, it overrides the previous update with the latest one, which leads us back to square one, which is the problem where we're just having 11 likes in the end instead of the 12. So this is a snapshot, but again, most of these isolation levels will differ per database driver or management system. So for Postgres, it can be different from MySQL and etc. So now let's take a look at using the read committed. So only read data that has been committed by other transactions. So if I come here and wrap this up within that transaction, I'm using Kisoli, by the way, which is this one. So TypeSafe SQL, query builder for TypeScript. So you can code again the types introspected from the database, and well, you get full type safety as you can see here. So I can say db.transaction, then set isolation level, and then we can say read committed. And then we can say execute, and then we get this callback and we get access to the transaction. So I'll comment all of this out, and instead we can copy this whole logic actually. So paste it here, then uncomment all of this, return the result from the transaction, and then replace the database calls with the transaction instead. Now if I save this and actually reset the likes or the views, so here where we say patch, as you can see I'm updating it to set the views to 0 for testing purposes. So curl x patch and then post views reset, and then if I get it, as we can see we get one view. Now if we say AB then 100 and do the same, as we can see it finished, and now if I get the posts, we get 19 views. What if we change this to serializable? So set isolation level to serializable, save this, and then let's do the same. So patch, then get, it's 1, and then we perform this. So it should be 101. We now get 33 views. So if we take a look at the official documentation on transactions for PostgreSQL, as we can see, PostgreSQL uses predicate locking, which means that it keeps logs which allow it to determine when a write would have had an impact on the results of a previous read from a concurrent transaction had it run first. And then it says these logs do not cause any blocking and therefore cannot play any part in causing a deadlock. And this is the underlying issue. It is not locking down that row, so well, the other concurrent transactions are still updating it just fine based on the stale data. So what can we do in this case? Well, for that, we can use logs in the application level. So for this, I installed this library called async-mutex, and then we can create const mutex is equal to new mutex, and with this, we can log this so that we can prevent anyone else from updating the row if it hasn't finished updating. So what we can do is say return, and then mutex, and then dot, and then we can say run exclusive, and then we can pass in an asynchronous callback function, and then we can just return from this. So let me get rid of this and close this down. And as we can see, we wrapped up everything within this run exclusive method. So whatever we return from here is going to ultimately be returned from this call. And what this is going to do is again, lock it. So it is going to check if this is the first time it gets a request and it is performing this, then it is going to acquire the lock and it is going to run the code. Now let's say another request came in and tries to access, well, the same resource. It sees that there's a lock present. So instead of throwing an error and saying, hey, you cannot do this because it's locked, it actually adds it to a queue. So once the first one is done with this, it is going to now invoke the other callback that pertains returns to the second call, and so on and so forth, because, well, it's a queue. It is going to queue them up, and it is going to make sure that they are executed sequentially, which is pivotal to prevent data races. So if we do this and then say AB, we run this, and then we get the data. As we can see, views is 101. We got that extra one because, well, we just performed a get, but the 100 do pertain to this benchmark call right here. And in fact, with this, we can get rid of the transaction. It's not needed for this particular case, so we can just copy this, and we just reference the database client itself without the transaction. And so we achieve the same result, and we avoid the overhead of the transaction. Obviously, do not get me wrong, this is never a substitute for a transaction. This is because we're not performing updates or deletes that should be rolled back in case of an error. So for us to better understand how these work, I recreated the Mutex class, but obviously bare bones. It is not as complicated as it is. If you take a look at the source code, you'll see that it has way more nuances. But with this, we can get the gist of it. So here we just define isLocked, which is a flag, so true or false. And then we have the queue, which is an array of functions that do not return anything and do not take in anything. And we'll see why. And then we have the constructor, this.isLocked is equal to false, and then this.queue is equal to an empty array. Now, if I scroll down, we have the run exclusive, which is the same as we're doing here. So mutex.run exclusive, and we pass in this asynchronous callback. So that's how it works. We take in a task, which must be asynchronous, of course, otherwise it wouldn't make much sense. And then we have the promise of t, and this well returns the promise of t. So we preserve the types. But here's the interesting part. We say await this.lock, and we invoke this method. Now notice how this returns a promise, and we know a promise has 3 states, so pending, resolved, or rejected. So in this case, we just check if it is currently locked. If it is, then set it to true, so that we now acquire this lock, and then we invoke resolve. And as we know, once it is resolved, this await is successful, so it proceeds with the execution for this method. So here we have this try finally, and we just wrap this up, so await task, and we return the result if it is successful, and if not, we do not care. We just say this.unlock, and this is pivotal for not causing a deadlock, so we do not lock down the whole application if this function threw an error, and so you wouldn't be able to run exclusive anymore, so that would be terrible. So we need to make sure to call this in the finally block. But notice how we're not passing the task itself. You might think, okay, the queue contains the task, but that isn't the case. We're just pushing the resolve function. That's about it. The reason we do this is because the mutex shouldn't be worried about the execution of the tasks themselves. The mutex is just worried about providing an easy access to a lock. So it wouldn't be ideal for it to also manage the execution and the queuing for the tasks themselves. It only worries about the locks, and that's the essential part. So we push this to the queue, and once we get the result from the task, so the current task that is locking down everything, we call this.unlock, and we check the length of the queue. So if it is greater than 0, then we just call this.queue.shift, which is going to remove that element. We get it here, so the next resolve, and well, if it exists, we invoke it. So now it can proceed with the execution. Otherwise, it is going to set it to false because there are no tasks in queue, so we can acquire the lock whenever we want. So this is how it works, but let's try it out. So let me comment this out, and then const mutex is equal to my mutex. And let's save this, and let's reset the database, and then get, as we can see, we get 1. And if I call this, everything runs successfully, and we get 102. So it is working as we expected to. So now this wraps up the video. I would really recommend taking a look at the source code for the async-mutex library. You will learn a lot. Anyway, I hope you learned a lot and enjoyed the video. And if you want to see more content like this, make sure to like the video and subscribe. I'll see you in the next one.